Hi, and welcome to our next video in trigonometry. In the previous video we looked at radian measure, and one area of mathematics where radian measure makes life immediately a bit easier is when you're looking at arcs and sectors. So let's have a go at those. So what we're going to do is have a look at the formula that we get for the length of an arc and the area of a sector when you're using radians, and then also do a little bit of problem solving when we are working in radians rather than in degrees. So here we go. So there's my sector. We have got an angle theta at the middle. We've got the radius is r, and we've got the length of the curved section of our sector is L. And previously, that's the formula that you're familiar with. We take the fraction of the circle, times it by the circumference. Similarly, for the area, there we go. Again, we've got the fraction of the circle times by the formula for the area. Those two things are currently in degrees, as indicated by the theta. I'll get my teeth out of the way in a second. Theta divided by 360. So what we're going to do is replace the 360 with the equivalent in radians, which we saw last time was 2 pi. So if I take this one first, our formula for the length, there we go, we've got exactly the same thing, but now we're dealing with radian measure. This is still our fraction of our full circle, but when we're measuring theta using radians. And you can see straight away we're going to get a bit of cancelling going on. And so our formula for the length of the arc becomes very simply the radius times by the angle. Simple as that. If we apply exactly the same idea to the area formula, again you can see I've replaced the 360 with 2 pi. Again we can do a bit of cancelling, not quite so much here, the pi's will cancel out, and that leaves us with the area is the theta over 2, I've just written that as half, so we've got half r squared theta, which just simplifies things a little bit. So what that means is, let's say for example in our sector up here we've got a radius length 4 and we've got the angle is 1.5 radians. So that means the length L is just going to be r times theta, 4 times 1.5, which is 6 centimeters, and the area of that sector is going to be half r squared theta, so that's half 4 squared times by 1.5, and so that's 12 centimeters squared. And so that's nice and simple and easy to work with. Let's move on and have a look at the kind of thing you might get in an exam. And so what you're going to get is questions that mix up your knowledge of arcs and sectors with the radians, and also a bit of your kind of your standard trig chucked in for good measure, sine rule, cosine rule, area of a triangle, all those kind of things all piled in together. So we've got an emblem there that's made up of a triangle and a sector, and we've got to show that angle ABC is 1.76 radians as our first part, and then part B we've got to find the area of that emblem. So here we go, part A, we've got to find that ABC, that's the angle there, and you'll notice straight away that in order to be able to find that angle there, I'd need, hopefully you can see my case, I'd need the opposite side, which I don't have, but you know what, I do have enough information. I've got a pair of opposite side angles there, so I can use sine rule, and that will allow me to find that angle at the top there, and then from there I can get to the angle that I'm after. So let's do a sine rule job on that. So sine rule, we need to find an angle, so let's put the angles on the top. So sine c over phi is sine 0.6 over 4. Making sure, of course, that your calculator is in radians. Bit of rearranging, sine c equals 5 sine 0.6 over 4. So c will be sine to the minus 1 of all of that. That's a calculator in radians, and that gives us an angle of 0.783. And again, you've got to be a bit careful because we're used to seeing angles being quite potentially large numbers. Now we're seeing angles that are quite small, they're decimals. And so I remember when I was just, I used to get mixed up between when I had to do the sine of the angle or when I'd actually got the angle myself, because both were decimal values. It takes a bit of getting used to, but you will get there. So what we've got is our angle there is 0.783. So that's angle C. So clearly what we've got to do now is use the old angles in the triangle add up to 180. In this case we've got angles in the triangle add up to pi, because we're working in radians. So we've got pi minus 0.6 minus the 0.783, and there's our 1.76, correct to 3 significant figures. Okay, on we go. Find the area of the emblem. That's clearly going to be the area of the triangle. So triangle ABC plus the sector BCD. So let's do those as two separate bits. Triangle ABC, there it is. So that's quite straightforward. Half AB sine C again working in radians with the 1.6 we got from the first part of the question. So that's why that part A was a show that. So that still allows you to do part B. So we've got half times 5 times 4 times the sine of 1.76. So the area of our triangle is going to be 9.82 centimeters squared. So let's pop that to one side. That's that bit done. And let's now have a look at the sector. And there it is. So that's sector BCD. And clearly we need to know the angle at B. Well, we can get at that because we know that the angle in the triangle at B was 1.76. That's what we had previously. So to work out that angle there, which is CBD, all we need to do is the 180 minus, but we're in radians, so it's pi minus 1.76. So that gives us 1.38 for that angle there. And now that we've got that, we just need to plug it into our formula, half r squared theta, with r being 4, theta 1.38. In it goes, and there's the area of the sector. Final job is simply now just to add those two things together, and there we go, we've got our total area, 20.86 centimeters squared. So the fact that we're working radians doesn't really change anything massively. Same principles, your trig stuff still all works the same. It's just we've got simplified versions of the formulas for arcs and sectors, and you've just got to watch out when you're doing kind of your basic angle calculations that you are working in radians and that your calculator is in radians. On we go. Here's another example of where using radian measure just simplifies things a little bit. The old standard shaded area in between the triangle and the sector. So we've got the triangle OAC and we've got the sector OABC, and we need that kind of green bit in between, and we've got to show that it's half r squared theta minus sine theta. So off we go. Segment ABC is going to be the difference between sector OABC and the triangle OAC. So let's kick off with the sector OABC, which is going to be our half r squared theta, and we can't do any more with that because we're just dealing with it in its generic form, so that's that bit sorted. Let's now go for triangle OAC. There's our formula for the area of the triangle. A and B, the sides of the triangle, they're both going to be r, so I've got half r times sine theta, and so that is going to be half r squared sine theta when you tidy it up. And now let's do the subtraction. There it is, and straight away you can see we can do a bit of factorising that's clear from the expression that we're trying to work towards. We can take out half r squared, and when we do that we end up with the result that we're looking for, and there we go.